Welcome to another video over linear analysis. In this video, we are going to take a look at the beautiful, wonderful, amazing world of piecewise functions. So let's be honest, linear functions all by themselves are pretty boring. Their domain is all real numbers. Their range is all real numbers. They have no min, they have no max. They're always increasing, they're always decreasing. They have a constant rate of change. All of these things are very, simple and boring. So how can we make linear functions harder and more fun? More things we could do with? Well, piecewise functions, that's the trick. So let's quickly show you a piecewise function, remind you what they are. So a piecewise function is one function that's made up of a bunch of pieces. So on the left-hand side here, we have the different pieces. So this function is made up of negative 2x minus 3. That's going to be a linear function going down because it has a negative slope. Negative 1, which is a really simple, boring horizontal line function at negative 1. And 1/4 x minus 3/2, which is a increasing function with a slope of 1/4. So we're putting all three of these functions together, but we only use the pieces at certain times, and that's what the part on the right is for. So this tells you when to specifically use each piece. So for example, the top piece is only used if x is less than or equal to negative 1. The middle piece is used if x is anywhere between negative 1 and 2, but not equal to negative 1 or 2. And the bottom piece is used when x is greater than or equal to 2. So this basically dictates what you use, right? So if I say, hey, what is f of 5? Well, you're going to say, well, okay, 5 is greater than 2. So I'm going to use this bottom piece. So it'd be 1/4 times 5 minus 3/2. That's going to be 5/4 minus 3/2. And I love fractions, so I'm going to convert this 3/2, multiply both by 2, so that's 6/4, right? It's the same thing. 5/4 minus 6/4 is negative 1/4. Boom, there is my output. So again, when you're asked to evaluate this overall piecewise function, you need to look at the directions on the right that tell you what piece to use. But graphing these functions is where it becomes really fun. So here are the three different pieces of this function. So the red is the first piece when x is less than negative 1. So I'm going to put a line down here at negative 1. So you'll notice anywhere below negative 1, we use that red piece. From negative 1 to 2, we use that horizontal line at negative 1. So you see that horizontal line there. And at anything greater than 2, we see this increasing linear function with a slope of 1/4. So, you put it all together. Here are the individual pieces, red, orange, and green, and they all come together to make the piecewise function. So now this function just gives us so much more to talk about, right? So we could say, what's the domain? Well, look at the graph. The domain is still negative infinity to infinity. I'm allowed to plug in any number I want. Now, if x is negative 1, I'm going to use the top, not the middle, because the top says less than or equal to negative 1. And if x is 2, I'm going to use the bottom, not the middle, because the bottom is for greater than or equal to. You get the point. So it just gives us so much more to talk about. So the domain is all real numbers, negative infinity to infinity. Now the range actually changes here because notice that the graph is kind of pieced together where there's nothing below negative 1. So the range would actually be negative 1 towards infinity. So they're looking from top to bottom, left or up to down, I guess, or down to up. The graph starts at negative 1 in terms of y values, and it goes all the way up forever because of the end behavior. Hey, might as well talk about end behavior real quick, right? What is the limit of this function as x goes towards negative infinity? So if we're looking at the left end of the graph, it's going towards infinity. It's going up forever. And what is the limit as x goes towards positive infinity for this function? What is the limit on the right end behavior? Well, it looks like it's going up. Now it's going up at a slower rate. The rate is 1/4, but it's still going to go up towards positive infinity forever. So here we see two end behaviors that are the same. Also, increasing, decreasing, and constant, those intervals actually change. So the graph is decreasing over here. So we would say the graph is decreasing from negative infinity to negative 1. So on this interval from negative infinity to negative 1, the graph is going down. So, that's an interval for x, by the way, right? So if x has any value from negative infinity to negative 1, the graph will be on a downward decreasing motion. The graph is going to be constant from negative 1 to 2. So in that interval right here from negative 1 to 2, we see that the graph is staying constant. And then the graph is increasing from positive 2 towards infinity. So from 2 to infinity, the graph is a linear function moving up. So that's an increasing graph. So again, it just gives us so much more to talk about. Now, how about extremas, any mins or maxes? Not really, because every point on here, I mean, technically -1 is the lowest you're ever going to go, right? All of these values down here at -1. I'm just going to erase that. It's looking kind of crappy, all my markings. But, you know, an extrema is a single point that's lower than everybody else. And there's actually infinite points on this orange line that are all minimum. So there isn't one single point that's lower than all others. But -1 would be the lowest output, you put it that way. Other cool things to talk about are continuity, right? So we know linear functions are always continuous. So each of these graphs all by themselves are continuous everywhere. But when we piece them together, where they get pieced together is where there might be some issues with continuity. So those are kind of the cool pieces to check. So how do you know where they come together? Well, you could look at the graph, and I have the beautiful covers here so you to see they come together at -1. When x equals -1, they come together. And the green and the orange come together at 2. But you also see that right here, right? So at -1 is where you switch from one graph to the other, or one function to the other. And then at +2 is where you also make a switch. So those are usually places where we like to just kind of check for continuity to make sure everything's okay. So let's check -1. So is there a point at -1? If you plug -1 into this function, do you get a point? Well, I am allowed to plug -1 into this function right here because it says that is what you use if x is less than or equal to -1. And -2 times -1 is +4. 4 minus 3 is 1. So at -1, oh, I did that wrong. I'm sorry. I think I said the wrong mathing there. So -2 times -1 is +2. 2 minus 3 is -1. So we do see a nice, beautiful filled in point right here at -1, -1. And then remember, we like to look at the left side and the right side. We talk about continuity, right? So what is the limit as we approach it from the left and the right? We need those two arrows to be coming together, and they are coming together. That's awesome. Where are they coming together at? -1. So that is why the limit as x approaches -1, sorry for my messy handwriting, is also -1. So there's a point at -1. That's the y value I'm talking about, -1. There is a limit. Both arrows from the left and the right side are coming together at -1. It's all continuous. It's so nice. And obviously, we can see the same thing happening here too, right? When we plug 2 into the function, that's using the bottom right here because x is greater than or equal to 2. And we get -1 as the output. That's why there's a nice point right there. The left side and the right side, so the limit as we approach 2 is also -1, right? The left side and the right side are going to -1. The two arrows are coming together. There's a point there at -1. Voila, we have beautiful continuity at 2. But again, when we piece different linear functions together, it just makes it a lot more fun to talk about. Here's another one. Pretty cool, interesting, right? So check this one out. When x does not equal 2, so for any value other than 2, right? I mean, literally every number other than 2, we're going to use the function 3x plus 1. But if x does in fact equal 2, the function is stated to not exist. So what the heck would that look like? Well, we're basically going to be a line. We're going to be 3x plus 1, which is a increasing line with a slope of 3. Everywhere except 2. So when x does equal 2, we need to put something there that indicates that, well, nothing is there. It does not exist, and that's where we get a hole. So here's a beautiful picture of this function. So the green line is the 3x plus 1. And then we see when x equals 2 right here, if I put like a line right there at x equals 2, we see that there's nothing there. I had to put a hole there, an open circle, because there's nothing there. The function stated that when x does equal 2, we need to not exist. So literally nothing is there. This is awesome. So again, this gives us a lot of stuff to talk about. So basically, I cannot include 2 in any of my answers. So if I say, what's the domain? The domain would be -infinity to 2, and then union 2 to infinity, because at 2, the function does not exist. So I need to make sure I skip that in my domain. In the range, R for range, so I'm thinking y values here. So it looks like 7 is what's getting skipped. So it'd be -infinity to 7, union 7 to infinity. There is nothing at 7. The function is always increasing, right? But at 2, nothing's happening. So it's increasing from -infinity to 2, and then from 2 to infinity. Because again, I can't include 2 in the interval for increasing when at 2, nothing is happening. So you've got to really kind of think a little bit more when you have these weird piecewise functions. Now, end behavior, the left end's going down towards negative infinity. The right end is going up towards positive infinity. That's all pretty easy. But let's talk about continuity. That's kind of the big point for this particular graph, because this is a great example where we see at 2, we're not continuous, right? At 2, the graph doesn't continue through. There's a hole there. So how can we prove that? Well, remember, there's kind of 3 things you got to check for continuity. First, you got to figure out what happens at 2. Okay, so what happens at 2? Well, when x equals 2, the graph does not exist. So right there is a reason why we are not continuous. So we could easily say x is not continuous at 2. It's continuous everywhere else, but just not 2. But let's talk a little bit more about the limit, right? What is the limit as x approaches 2 for this function? This is going to be kind of cool to think about. So this is where we say, okay, I'm a little person, I'm walking on this function, and as I get closer and closer to 2, there I am, and I got to check both sides, the left side and the right side. So I realize that as I get closer and closer to 2, the left side and the right side are coming together, right? Now, at 2, there's a hole, nothing. I get that. But remember, a limit's not asking you what happens at 2, it's asking you what happens as you approach 2. And as I approach 2, the left side and the right side are coming together at 7, like they are, right? Now, they're never going to get to 7 because nothing is there, but they're getting closer to 7. And that's the whole point of limits. And I know that's a lot to take in. I know limits are a little bit new, but this is the idea, is that as we get closer and closer and closer to 2 from the left side and the right side, yes, at 2, there's nothing, but as we get closer, the function's trying to get to 7. So think of like limits as like it's trying to get to 7, but it just can't get there. So that is another reason why we're not continuous, because remember, in the definition, we need these 2 values to be the same. Well, they're clearly not. One doesn't even exist and one is 7, so that's again why we're not continuous at 2. All right, here's another cool piecewise function. So this one tells us to use the linear function. It's a decreasing function with a slope of negative 6/5 x plus 2. Anywhere x does not equal 5, and then when x does equal 5, they want us to use 1. Now, here's a kind of a thing I want you to do, right? I actually want to plug 5 in to our function. Now you might be like, well, wait a minute, why am I plugging 5 into the function when it says do not use this when x equals 5? Because I just want to prove to something that, it's going to leave a hole, basically. You'll see that when I look at the graph in 1 second. If I plug in 5, let's see how I get the 5 is reduced to a 1. I get negative 6 plus 2. Negative 6 plus 2 is negative 4. So this function is supposed to have a point at 5, 4. Negative 4, excuse me. That's what's supposed to happen. But the way I've defined this cool, interesting piecewise function is that when x equals 5, don't use that function. So don't do what I just did. Instead, when x equals 5, use 1. So check out what this graph's going to look like. So here we see this beautiful, nice, simple linear function with a slope of negative 6/5. But notice what's happening at 5. At 5, I'm supposed to be down here at negative 4. That's where I'm supposed to be. But the function said, no. If x equals 5, don't use that function. Make a point at 5, 1. So there's my point at 5, 1, because if x equals 5, I'm supposed to be at 1, according to the piecewise function. But that left a gaping hole at 5, negative 4. So lots of cool things to talk about. The graph is decreasing everywhere, except for 5. End behavior, that's easy. Left end's going up towards infinity, right end's going down towards negative infinity. That's all pretty simple. No mins, no maxes. We get all that, right? Because linear functions are pretty boring. But let's talk about continuity. So first thing I'm going to say is what happens at 5? Well, in the previous problem, we saw DNE, but not here, right? At 5, we do have a solid point. When x equals 5, the function equals 1. That's exactly what the function's telling us. When x equals 5, spit out an output of 1. Who cares what this other function says? No, we're using 1. Okay, so we see that point right there. But then we say, okay, well, what about the limit as x approaches 5 for this function? So that's where we say, okay, so, I like to put that dotted line at x equals 5. And I say, okay, let's follow the graph. Let's be a little person following the graph. And as we get closer from the left and as we get closer from the right, the 2 sides are coming together, and they're coming together at negative 4, right? Remember, it's about where we're getting closer to. So as x approaches 5 from both sides, I'm getting closer to negative 4, but the moment I am 5, I jump up here to 1. And again, this is a great example of non-continuity. I'm not continuous at 5 because I have this displaced point, right? The point got moved. It was supposed to be at 5, -4, but I moved it to 5, 1. So now the function exists at 5. It does. It's right there. You see this point right there. The limit exists. The two arrows from the left and the right are coming together at -4. But those two things are supposed to be equal, right? They're supposed to be equal for continuity. And that makes everything continuous and beautiful. And I just don't have that here. All right, here's another one that gets even a little more kind of weird and ugly, but this is cool, right? So I got 3 pieces. I got a linear function with the slope of 1/4. I got a horizontal function at 5, and I got a negative decreasing linear function. And again, here's all the different places I'm supposed to use these numbers. So a couple of things I want you to notice here is I'm supposed to use this top function if x is less than -4. Okay, lots of numbers are less than -4. Or between -4 and 1, but not including -4. But you do include 1. So the first thing I notice here is that what do I do if x equals -4? Like, if you actually understand how piecewise functions work, I'm not allowed to use -4. Because if x is equal to -4, I'm not supposed to use this because that's only for less than -4. I'm not supposed to use this because that's between -4 and 1, not including -4. So this is where, like, if you try to plug -4 into this function, you get does not exist, because based on the rules, you're not allowed to use -4. Like, you literally can't use it, and that's what produces a DNE. So here is a picture of this function. Actually, I'm going to use this one. It's a little bit nicer because I have both the function and the graph here. So first off, on the left-hand side in green, you do see this beautiful function, 1/4 x plus 3. Really nice, simple. It has a slope of 1/4 and has a y-intercept of 3. So cool, so simple to see. But check out -4. At -4, there's nothing. I had to leave a hole there because, again, based on the rules, I was not allowed to use -4 as an input. That's going to produce a hole, another discontinuity. And then check out between 1 and 4, I'm using 5. That's a horizontal line at 5. So you see that right there in purple. And then if x is anything greater than or equal to 4, we see this decreasing linear line, -2x plus 13. So a couple cool things that we see here for the first time is we see what we call a jump. So right here at x equals 1, hope everybody sees this jump. So what that means is that where the graph came together, right? So we got 3 different functions here. The first 2 come together at 1 because that's where they meet up. And the second 2 come together at 4, right? So you clearly see the first 2 graphs meet at 1 and the second 2 graphs meet at 5. But the issue is when x equals 1, they don't, it's like you're stitching, right? You're sewing and the stitches don't come together. So if I plug 1 into the first function, I have 1/4 x, which is 1. So 1/4 times 1 plus 3. That's going to be 1/4 plus 3. 3 could be viewed as 12/4. Just trying to get my common denominator there. And that's going to be 13/4. So that's where I am at right here. 13/4 is a little bit more than 3. So that's where we see this value right here. But then it makes a jump right after 1, because if x is anything greater than 1, we're going to use the horizontal 5. So that jumps me up to 5. So you'll see that when x equals 1, the 2 parts don't get stitched together nicely. The one side's down at 13/4, the other side's up at 5, and they just don't come together, which creates, guess what, a discontinuity. However, at 4, they do come together. Like, look at this. You could see it in the graph. They come together beautifully. If I plug 4 into this bottom function, I get -2 times 4 plus 13. -2 times 4 is -8. -8 plus 13 is 5. So the horizontal line is 5, obviously, so it ends at 5. But then where this new function, -2x plus 13, picks up, it's at 5. So everything comes together beautifully. So that would be an example of continuity, right? There's no hole there. There's no jump there. It's nice and continuous. So again, if I ask you, where is this graph not continuous? The first place would be -4. We clearly see that at -4, nothing exists. And again, we could go through the process, right? But the very first check for continuity fails. Is there a point at -4? And the answer is no. It does not exist. Now let's talk about the limit real quick. As we approach -4 from the left, and as we approach -4 from the right, those two arrows are coming together at 2, like they're trying to get to 2, but they never actually get there, which creates the discontinuity. And then let's check 1 as well, right? So let's ask ourselves a couple questions. What happens at 1? Okay, is x allowed to equal 1? Yes. Let me erase this so I kind of get this mess out of the way here. So is x allowed to equal 1? Yes, right here. This says if x is anywhere greater than -4 or less than or equal to 1, use this top function. So if I plug 1 into the top function, actually I already did that over here, 1/4 times 1 plus 3, 1/4 plus 12/4 is 13/4. So I do get a value. That's awesome. I do get 13/4. But then we ask the question, what about the limit? What is the limit as x approaches 1 for this function? This is where we run into a problem. The left side is down here, okay, right? If I'm up, and draw that dotted line, that helps some students. As I approach 1 from the left, I'm down here. As I approach 1 from the right, I'm up here. My two arrows aren't coming together. The left side is at 13/4. The right side is at 5. They're not coming together, so the limit does not exist. Because for a limit to exist, the two sides have to be trying to meet. And that's actually really important for you to hear. Right, whoop, I did not mean to do that. Look right here real quick, right? Right here, we have a limit that does exist. The limit as we approach -4 is 2. The left side and the right side are coming together. And they're trying to get to the same value of 2. So the limit does exist there. The problem is there's no point there. And that's why we fail continuity. But for the limit question alone, the limit does exist. Okay, because remember, I've said this before, I'll say it again. And I know this is brand new, which is why it's going to take a little bit of time, but a limit is not asking you what happens at a particular value. It's asking you what happens as you get closer. And as I get closer to -4 from the left, from the right, I am trying to come together to 2. I never get there, but I'm trying. They're coming together to 2. The two sides are meeting up. So that's why the limit does exist. Whereas when we look at 1, the left side is at 13/4. The right side is up at 5. They're not coming together. They need to meet, but they're not meeting up. So the limit fails to exist. So of course we have a discontinuity. I mean, ultimately, I hope, it may take some time, but ultimately I hope you do learn about continuity and how we check it with limits and all that fun stuff. But if you think about it, if you have to lift up your marker or your pen or your pencil to draw the function, you're not continuous there. So if I'm saying, hey, I'm going to try to draw this, I'm trying to draw this, I'm trying to draw this. Oh no, a hole. I have to lift up my marker. That means you cannot be continuous at -4. And then I'm drawing. Uh-oh, I have to lift up my marker to continue drawing. If you have to lift up your marker, you're not continuous. But notice here, I don't have to lift up my marker. I make a nice smooth turn. I was 5 and then I start to fall. So right here, it was nice and smooth. It was continuous. But at -4, I had to lift up my pencil, and at +1, I had to lift up my pencil. So at those two places, I'm not continuous. All right, so piecewise functions really just allow us to make way more interesting functions that give us way more cool stuff to talk about. And I'm pretty confident you guys can answer questions like domain and range. You know what? Might as well do it real quick for this problem, just since we're on track here. So, if I said, what is the domain of this function? Well, it'd be -infinity to -4 because nothing happens at -4. And then it would be -4 to infinity, right? Because every value after -4 does get hit. Now at 1, I'm discontinuous, but there is a point at 1. Like the domain is just saying, hey, is there a point at that value? And at 1, sure, there's a point. At -4, there is no point. So I had to skip -4, but everywhere else, there is a point. The discontinuity is a separate topic from domain and clearly not continuous at 1, but there is a point at 1, and that's all the domain cares about. So anyway, I think that stuff is fairly easy, but this new idea of continuity, I hope you get it. It's really easy to see in a picture, but we might have to practice the idea of trying to prove it and make sure we explain with the math notation of limits and so forth why it does or does not exist. All right, so that's it for this video. Hopefully you learned a lot more about piecewise functions and how they look and how you could graph them and how we could take pieces of multiple linear functions and put them together. All right, see you guys later.